Data placement strategies. Replication strategy is of two types, simple strategy and network topology strategy. In the simple strategy uses the partitioner, of which there are two kinds of partitioner. One is called random partitioner and the other one is called byte order partitioner. Random partitioner is COT like hash partitioning, and whereas the byte order partitioner assigns the ranges of keys to the servers, and it is easier for the range queries. For example, let me call all the Twitter users starting with A to B, but instead of going for a byte order partitioner, random partitioner is a recommended partitioner. Why? Because random partitioner partitions the keys uniformly across all the servers. And it is more efficient to use the random partitioner, whereas the byte order partitioner will have the various issues that after so many number of storage and operations, what will happen? It will form the hotspots out of this write operations. So, hotspots will create problems, and again load balancing has to be done and so on and so forth. So, it is recommended that the random partitioner is being used in most of the cases as far as the simple strategy is concerned. Now, another strategy for the replication is called a network topology strategy. So, network topology strategy for data placement requires for multiple data center deployments or considers multiple data center deployments. So, for example, network topology strategy will use 2 replicas per data center. So, if there are 3 data centers, then it requires 2 replicas per data center, that means 6 replicas it will be there across different data centers. Similarly, when there will be 3 replica per data center, and if we have 3 different data center, so 9 different replicas will be there across all the data centers. Now, in per data center replication or data placement strategies will be doing that. First replica will be placed according to the partitioner and then go clockwise around the ring until you hit a different rack. So, storing the replicas on a different rack ensures the rack failure tolerant it ensures the rack failure tolerance. So, that means what we have seen is that when we go for the network topology strategy, we are placing our replicas in different data center. If there is a multiple data center deployments or geographically distributed data centers, if they are there, then these replicas are stored across these data centers, and this particular things can be achieved using the partitioner. What partitioner will do? For example, there are different data centers. Let us assume that in your multi data center deployments there are 3 data centers which are shown in the figure. So, what it does is the first replica will be placed, the partitioner will place the first replica here. First replica will be placed according to the partitioner. Let us use the 2 replica per data center. So, and the other replica will be placed on the ring, and the second replica will be placed so that this replica 1 and 2, this replica 1 and 2, they resides on a different rack. Similarly, this partitioner will also store on these 2 replicas on the other data center and also on other data center. Now, you see that different data centers have a ring and there will be a coordinator which will coordinate among themselves. So, this particular partitioner has to contact to these coordinators and they will in turn carry out this network topology strategy based the data placement in this manner. Now, the next issue in this system is called the mapping of IP to the racks and data center. So, the first thing is about key to the server. So, this we have seen key to the server mapping in the previous slide. Now, we are going to see the another design issue which is called how the IPs are to be mapped to the racks and data center. So, the mapping of IPs to the racks and data center is done through the technique which is called a snitches. So, this particular configuration is can be done in a file which is called a Cassandra.yaml configuration file, and let us see these technique which is called the snitches, which does this mapping of IP to the racks and data center. So, there are different type of snitches. The first type of snitch is called the simple snitch. Simple snitch is unaware of the topology and it is rack unaware. So, that means it will be done in a manner which will be a random assignment and does not have any inference or does not have any information about from looking from the IP addresses where it is going to be mapped on, is called simple snitch. The other type of snitch is called the rack inferring snitch, which assumes the topology of the network by an octet of server IP addresses. So, for example, if this IP address is there 101.102.103.104, this infers that the first octet is not going to be used for any inference. The second octet represents the data center address and third octet represents the rack octet and the fourth one is the node octet. So, if let us say that, for example, if let us say the IP addresses is let us say 101.102 and 104.102, that means both these IP addresses they are mapped to the same data center. Similarly, we can see that 102.103 and 104, that means within that data center they are referring to the different racks, and within the rack if let us say that the fourth octet becomes the node octet. So, this way the IP addresses will be able to infer about the topology if it is used in this snitch, which is called rack inferring snitch. Another type of snitch is called the property file snitch, which uses the configuration file, and fourth type of snitch is used in the EC2 snitch, and which is used in EC2 type of storage system, that is the cloud storage system. So, EC2 has two kind of inferencing. One is the EC2 region, which will tell about the which data center is used to store the data. The other is called availability zone, and which will tell about which rack uses which rack is used to store the data. So, if it is used the EC2 based the cloud system. There are various other snitches options are available. So, we have just introduced some of the most commonly used snitches used in the Cassandra. Now, we are going to see the operations which are supported in the Cassandra in the form of write operations. So, as we have seen that the writes has to be lightning fast writes, which is supported by the Cassandra because it is write heavy workloads. So, let us see how the Cassandra supports the write operations. So, the writes need to be lock free and fast, hence it does not require, the write does not require to be to read or to perform a disk access before performing the write operations. And the client sends the write to one of the coordinator node in the Cassandra cluster, like we have seen in the previous slide, that one of the server becomes the coordinator and the client will send the write operation to the coordinator, and the coordinator will perform this write operation. So, coordinator may be a per key basis or a per client basis or a per query basis. It depends upon different use cases and applications, and all these variations are possible for the coordinator. So, per key coordinator ensures the write for the keys are serialized. So, that means for per key coordinator will ensure that the writes, all the writes which performed over that particular coordinator for per key basis, they are all serialized, and this ensures the consistency in some of the cases that we will see in some of the applications where it is wherever it is required to be useful. The next thing is about the coordinator uses the partitioner to send the queries to all the replica nodes responsible for the key. So, this particular coordinator will now send using partitioner to send the queries to all the replicas responsible for the key, where the keys are stored. Now, when x of these replicas out of them, if out of them, out of n, let us say n replicas, and x replies back, what is this x number is? When x replies or responds, the coordinator returns an acknowledgement to the client. So, what is this value of x which is acceptable, that we will see in the further slides. Now, write operation, we are seeing that this way always writable, that means write operation always is performed and which applies or using the hinted handoff mechanism. So, what is this hinted handoff mechanism to basically which uses which is used for the write operation that we are going to see now. So, if a replica is down, the coordinator writes to all other replicas. Let us understand the same diagram, that if this is a partitioner and these are all, let us say there are 3 different replicas, and if this wants to write, so if any of these replica, let us say this replica is down, the coordinator writes to all other replica and keeps the write locally until the down replica comes up. So, for this replica which is down, the coordinator himself keeps the values at its end, and whereas it will send it to all other replicas these values. If the replica is down, the coordinator writes to all other replica and keeps the write locally down until the down replica comes up and backs up. When all the replicas are down, let us say, then the coordinator will buffer all the write operations at this end and wait for up to the few hours till these replicas which are down, they may come up and they may get the updates. So, this is called hinted handoff mechanism, and which is used to perform this always writable, and irrespective of the replicas are down or not, some are down or all are down, even then the write is performed and using the hinted handoff mechanism. So, we have explained that what do you mean by always writable. So, in this particular scenario using hinted handoff mechanism. Now, as far as we know that there is one ring per data center. So, per data center coordinator is elected to coordinate with other data center, and this election is done via the zookeeper, which runs a Paxos protocol. So, again we have already seen and discussed, for example, this is a 3 data center. So, every data center will have a coordinator, and these coordinators will communicate with each other. So, this coordinator, if they are elected using the zookeeper, and the zookeeper runs a Paxos consensus protocol. Now, writes at the replica nodes, we are going to see the details of it. Now, when a write is performed at the replica, so it will be done in this following manner. On receiving a write, it will be first logged in to the disk commit log to ensure the reliability, and in case if it is a failure of any kind, then it can be recovered from the failure. That is why it has to be first log into the disk commit log. Now, then it make changes to the appropriate mem table. So, mem table is an in memory representation of multiple key value pairs, and typically this particular mem table has append only data structure, therefore, it is fast to write in the mem table, and there is a cache that can be searched by the key. So, this is this is maintained in a cache, and therefore, it can be searched by the key. Therefore, these operations writing and searching is become fast if it is done through the mem table. Now, in mem table the operation is the write back, that means it will be stored in this in memory mem table, and then later on it will be written on the disk. Whereas another approach which is called write through, that means if it is written to be on write is to be done on the disk or to make a persistent, then basically it is going to be a time taken, and that process is called write through. But Cassandra by default supports the write back. So, it writes into the mem table, and that is it. So, hence the write operations are lightning fast by this method of using cache to do the to write the multiple key value pairs. Now, when the mem table becomes full or becomes old, then automatically it will be flushed to the disk at a later point of time. So, the data file will be stored in the form of the SS table. So, when it is done, then these data files are stored in the SS table, which is nothing but a list of key value pairs which are sorted by the key. So, in the cache the same thing is maintained that is called a mem table, and within the disk this particular same task is maintained in the form of SS table. So, the data file which is stored in a SS table, that is full form is called sorted string table, is a list of key value pairs and which are sorted by the key. So, SS tables are immutable, that is once created they do not change, and they are also maintaining an index file, so that search becomes fast. So, index file is associated with a SS table of which will indicate the key and the positions in the SS table pairs. So, that is maintained in the index for make it the retrieval a faster one. Now, to make it more efficient retrieval using SS table, a Bloom filter is introduced here in Cassandra. Bloom filter provides an efficient search through this SS table. Let us see what do you mean by the Bloom filter, how it enhances the efficiency for searching. So, Bloom filter is a compact way of representing a set of items, and in this data structure checking for the existence in the set, whether the element is present in the set is cheap. So, there some probability of false positives are there, that means an item which is not in the set may turns out to be true sometimes, but there will be never false negatives. So, that means if the item is not there, always it will say no with 100% confidence. In some of the cases even if the item is not present, even then it will say sometimes present, that is called false positives. The working of the Bloom filter is like this. So, whenever a key which required to be searched, we want to search a key through the Bloom filter, then it has to go through the k different hash functions, and every hash function will generate a bit, and this bit will be then inserted onto the large bit map. So, that means when it is written, then these bits are set, and when it is searched, then using hash function it will check whether all the bits are 1. If it is all the bits are 1, then it will say the item is present, although if it is not, then it will be a false positive. If it is 0 sum in one of these bits, then obviously it will be false negative, that means it is not inserted. So, when we insert a key into this, then all these index the large bit map will be set at all the bits, all the k bits. And if you want to check if it is present or not, these hash bits are being checked if it is 0 or 1. Well, if all are zeros, if some are zeros, then it will be basically it is not present, and sometimes these false positives will happen, and it will say it is present although it is not. And if we see the performance of this Bloom filter, the false positive rates are very less, that is 0.02 percentage, is very rare. So, that means it will give that means it will check or search with a high efficiency, and with a high probability it gives a correct method. Now, then coming back to the Cassandra again, we have discussed that means data updates will accumulate over the time, and SS tables and the log need to be compacted. Compaction is a process which will merge different SS tables and logs also together. So, the process of compaction merges SS table by merging updates for a key. It says that the different SS tables which are immutable now require to be merged, and all the data has to be made persistent, so that other operations becomes efficient. So, this particular compaction runs periodically and locally at each server, Now, let us see how the delete is supported. So, the delete operation do not delete the items right away, rather it adds a tombstone to the log, and when the eventually when compaction and counters a tombstone, it will delete these items. Now, let us see the read operation, which is supported in the Cassandra. Read is similar to the write, except the coordinator can contact X replicas maybe in the same rack. So, the coordinator sends the read to the replicas that have responded quickest in the past, and when X replica respond, the coordinator returns the latest timestamp value from among those X replicas. So, we will see what is the value of X and how we can exploit this in the efficiency and the design of different application systems. Now, the coordinator also fetches the values from other replicas, and it will check for the consistency in the background, initiating a read repair if the two values are different. This mechanism seeks to eventually bring up all the replicas up to date. So, at the replica we have to see that a row may be split across multiple SS table. That means the reads need to touch multiple SS tables sometimes, and therefore, the reads become slower than the writes, but still they are faster compared to the other traditional RDBMSs. So, therefore, that means multiple SS tables sometimes required to be accessed for the read operation to be made successful. That is why the compactation sometimes is useful. Now, we will see the membership in the sense that the nodes which are there in the form of a ring, they come up and they go down. So, any server in the cluster could be a coordinator. So, every server needs to maintain a list of other servers that are currently in the server, and this list need to be updated automatically as the server join, leaves and fails. So, the membership cluster membership is maintained in the form of a gossip, and this example shows that these heartbeat or these details are exchanged, and then based on that they are being updated. So, here we can see that this particular protocol, here the nodes periodically gossip their membership list, and on receive the local membership list is updated as shown over here. So, if any heartbeat is older than tfail node is marked as failed. So, here we can see that once node 2 receives this heartbeat from node 1, then it will try to compare. For example, it has not seen this 1020, so it will be now added with the latest timestamp. Similarly, 118 and 110 will be stored, and this 1011 is there. So, all these are different heartbeat counters. This is heartbeat counter, and these are the nodes addresses. So, the node addresses 1, 2, 3, 4, they are being updated with their heartbeat counts since they have last being seen over here. So, the node number 1 has more recent heartbeats over here. So, that value of the heartbeat is updated, and similarly for the node number 2, the value is not updated. So, because it has the information about the recent information, so it is not updated. Similarly, for node number 3, it is 1098, and this information is more recent. So, 1098 is updated with a recent timestamp, and the node number 4 is not going to be changed here in this case. So, this requires the current clock time, and the current clock time will be used to update the entries. So, this way the membership, so the node 2 knows that in this topology there are 4 different nodes which are working, and they are exchanging their heartbeats, and this is called the cluster membership, and the Cassandra uses the gossip based cluster membership. Now, suspicion mechanism which is there in Cassandra. So, suspicion mechanism to adaptively set the timeout based on underlying network and the failure behavior. So, accrual detector is the failure detector which outputs the value of phi, which is representing the suspicion, and application set an appropriate threshold. Phi will indicate the calculation for a member. So, it will be inter arrival times for the gossip messages, and in practice the this threshold is of 5, that is it's 10 to 15 seconds of a detection time. Now, let us compare the Cassandra with RDBMS. So, MySQL is one of the most popular RDBMS as on date, and if it is more than 50 GB of data, let us see the performance in MySQL. The writes are taking 300 millisecond on an average, read is taking 350 milliseconds on an average. If we compare it with Cassandra, where writes is lightning fast, that is it will be 0.12 milliseconds on an average. Similarly, reads are also very fast, that is 15 milliseconds on an average. So, orders of magnitude this Cassandra provides these operation writes and reads much faster. Now, let us compare what is the catch, what is the difference, how it is going to achieve such a fast writes and better reads, and what is the catch, and where the Cassandra is losing compared to the RDBMS, that we are going to see using the CAP theorem.